So let me remind you the end of my previous talk about standard matrix models. What was the result? Result was when we considering, one can consider model with Hermitian matrices with some potential. N is a large number, and matrices M are Hermitian n by n. And this model reproduce partition function of one can in some continuum limit, which means large n limit, will reproduce critical properties of minimal models, put it on a fluctuating surface. Minimal models, which means models with central charge, and basic points in this correspondence, I will just remind just without any proof, just reminding the steps. So one can calculate this partition function by use of so-called notion of orthogonal polynomials, which are polynomials with following properties. So for every function, every potential v, there are polynomials fulfilling this property for any n and m, running up from 1 to n. So simply using this definition, one can calculate W, effective potential, as a series of where this Fn is Hn plus 1, this H, divided by Hn. So one can calculate the partition function exactly and organize continuum limit in a way that K, the number of matrix element as Xi, and Fk divided by N as some f function f psi, then this object will become integral from 0 to 1, d psi 1 minus psi f psi. So then further, using some trivial properties of orthogonal polynomials, like lambda times Pn, if you multiply lambda by polynomial, you get another polynomial, and you can expand it by a full set of basic elements as polynomials, and therefore, for this case, it is this simple property. Then one can analyze the function d lambda sorry? Any v. Yes. It's defined. These polynomials that depend on v. It's a defining measure. It's kind of measure, integration measure for polynomial. Yeah. Yeah. Yes, of course. It depends on v. I'm just going to this point. that depending on V, we will get a different critical behavior. And then this different critical behavior will just define continuum limits for different models, different minimal models. Any odd, even order V. Any say, okay, any even order V. So V is in general looks like this G is a coupling constant, lambda square plus some lambda 4, 2 plus some coefficient lambda 6, some another number, say 6, I think, and so on. It depends on potential. This depends on potential of matrix model. So then analyzing calculating this integral by using of this recurrent properties of orthogonal polynomials, one can get some recurrent equation. Plugging where this property is for orthogonal polynomials and considering again continuum limit, in which we are interested, we will come to the equation of the following type. This coupling G multiplied by psi equal to some constant plus some function, W depending on F. This function can be calculated by use of potential. And if this function have a property, it depends on potential V. It has a property that it's equal constant plus, say, first m derivatives at some point Fc, first m derivatives of this potential is 0. It's a critical point of order m. So the next term here is a 1 over m, m's derivative at the point Fc. One can imagine that there is this type of potential, right? Then this object, from here you can get some singular behavior for F, plug in expression over there for W, and you will get that W over n squared behaves like G minus Gc minus G psi 2 minus gamma, where gamma is equal to 1 minus 1 over m. This m is exactly the same. So this means that we have that was demonstrated last time, I will not do it now. Again, that we have it's fit with the bosonic string picture, where the area is diverging at this point, and the index of divergence, which is called string susceptibility, gamma is equal to 1 over m. It was reproduced by this matrix model simply as a multi-critical point of some function, which is related with the potential in the matrix model in our original formulation. So this calculation shows that we have everything some internal geometry of the surface only. Nothing else exists here. Potential and the reproducing surface is no other information. We have set of minimal models, and no particular information from those was initially incorporated into the starting definition of matrix model. It was somehow coded in the potential as a critical behavior. But the last time I showed that we have a problem in that type of non-critical string model, that central charges always should be less than 1. And in a matrix model formulation, it's naturally appearing that central charge. All this picture works for minimal models where central charge is less than 1. It's 1 minus 6 divided by m, multiplied by m plus 1. So, but in reality, strings we have, yes. Because this object is producing minimal models considered on a fluctuating surface, and one can, from Liouville part of this of the action effective theory, which is Polyakov's theory for non-critical strings, you can extract analytically string susceptibility, which is coinciding with this one. So I was telling about that last time, therefore I would not like to repeat it. Yes, for doing first talk. It is coming from Liouville part of the conformal anomaly, from Liouville. If you analyze scaling properties of Liouville for minimal models, for any model, you will get that you can calculate string susceptibility in the case when C is less than 1, and we don't have any theory for C larger than 1 because everything becoming complex and there are problems for unitarity and so on. And that's only minimal models. In parallel, the people invented matrix formulation, which is totally different from original formulation of strings, and get the same results. In the third way, numerical calculation consider triangulated random surfaces with spins there corresponding to minimal models. Numerical calculation reproducing the same result. Not only for string susceptibility, there is a value of calculation, anomalous dimension of all operators there, everything is coinciding. And so there is a full understanding of the string, this type of string theory for minimal models with central charge less than 1. And what I would like to discuss now, can we and how we can try to cross this bound C equal to 1 in order to consider more realistic strings and what we should do for that. And is there any way, immediately I will say that analytically I don't know the answer, but what I'm going to demonstrate now, I'm going to formulate matrix model which is doing that and make some calculation of the important part of this matrix model calculation which is necessary to do in order to finally extract critical behavior. Then it will correspond to real models for models when central charge is more than 1. It means central charge effectively it's a dimension of space, right, where the objects are living. So it's for real. If more than 1 is a space 2-dimensional, 3-dimensional, 4-dimensional, any finite dimensional, different from 26 or 10 in supersymmetric case. If you remember all these analytic formulas for calculation of indexes, there were 2 square roots, 1 minus C and 25 minus C. In matrix, there is no way, simply this result. That's the point. In matrix model, you have a potential, and there's written everything. No notion about minimal model. But you imagine that this potential producing some function which has a multi-critical behavior. Then suddenly you observe that the index which give this object. Because from here you can calculate f, you see, invert this expression. You will get that f minus fc is behaved like gxc, xi minus g. Critical 1 over m. Plug this one to the continuum limit expression for the effective potential, and you will extract strings subsequently. That's coinciding with minimal models, and I'm happy. Nothing else. Nothing else. The next confirmation, but if you consider triangulation of surfaces and put the minimal models as a theory of spins, like a Potts model for some, and you will reproduce the same necessarily numbers. Nothing else exists in this formulation. I cannot, this natural question is appearing now immediately where I'm going to. If I would like to consider other integrable model, not only minimals, but any model, Heisenberg models, continuum limit which gives Vezuminov-Witten-Novikov, or Hubbard model, any model which has a critical point and where we have a conformal invariance. How to formulate the things in order, can we formulate matrix model which can give a string corresponding to that picture when you put on random fluctuating surface different objects, integrable models. How to do that? That's the talk now I'm going to do. So let me give you some a little information about integrable models. The basic element of integrable model is the so-called R matrix, which is an object which gives evolution of the states in 2 points. So you have a 2 linear spaces V. Those are the space of spins. It can be half spin or any spin S, then correspondingly you have a dimension of this linear space as 2S plus 1, which maps to another linear product. So, so you have 2 initial and 2 final states, and you have this type of object here. This is R matrix. This object has 2 initial indexes, alpha, alpha prime, and 2 final indexes, beta, beta prime. So alpha, alpha prime, beta, beta prime. So when you have this object, you construct, you have a spin chain, for example. At each point, you have a linear space V. And if you would like to define evolution of this chain now, you can be considering particular product of R matrices which are defined for every pair. You define so-called transfer matrix as a product of R matrices, particular product of R matrices. Which means I have to put index alpha, alpha prime here, beta, beta prime. Then another index is here, alpha 2 prime, beta 2 prime. It is better to write gamma. Here, gamma prime, and so on. So with repeating indexes here, there is a summation. This is the way, as a matrix multiplication, it's a way of multiplication of R matrices. Then this product will define evolution of the spin chain state into another, to one time, discrete time ahead. So T is mapping state of chain, product of spaces, Vi, into another state. This is a standard derivation of transfer matrices in algebraic beta ansatz. And then taking T, n order of T, and trace after that, you get partition function. In this way, all models of integrable models can be formulated, starting from R. So now, what will happen, the question, if somehow this object is, so if you imagine now the end order of T, you will get a regular lattice, you see? You will get a regular lattice, regular square lattice. What will happen now if from some point I will pick up particular R matrix and make a network, this network, random. I'm going to show that it will be equivalent of considering surface, random surface, where this R matrices are defined in a particular way. Namely, you can look at this picture. It's an example which coming from three-dimensionalizing model as a gauge theory. Considering three-dimensional regular lattice, any surface, which is this black one here, and consisting of these square faces. Now let's define the dual lattice by middle points of these squares. In every middle point of the link, let's put the point, connect them by red lines with the rows. You will get this dual lattice consisting of red lines with the rows, where in each square here, I'm imagining some R matrix is here. On each face, one can put here some R matrix, because any R matrix of this type, I can redraw some other way. I can make it some square with arrows. You see arrows coming, go here and come. I will join it straight. And what I get, that R matrix is corresponding to this type of picture with arrows. So you put these R matrices on the squares, and their indexes at each middle points, and there is a summation of R's where the index are common. For example, at this point, there are two R matrices have legs, this one, and there is a summation of corresponding indexes alpha attached to this point. So you will get formally some product of R's some product of R matrices associated with particular surface. Each shape of surface will define this product. This is defined by surface sigma. And then I will take sum over all surfaces. This partition function will give me theory for when this particular integrable model with R matrix is considered on a fluctuating surface like this. And I'm taking sum over all worldsheet surfaces in Polyakov quantization. So formally, this define just definition of the string theory with when this particular theory, integrable model with R matrix is considered on a fluctuating surface. But how to proceed further? To do that, let's consider now another matrix model, not that one which was written there, but I would like to separate in the potential now quadratic part of that potential. And I would like to express W as minus, say, 1/2. Okay, 1/2 is not needed. M alpha beta R alpha beta alpha prime beta prime M alpha prime beta prime. I'm considering Hermitian matrices, therefore I'm dropping notion of Hermitian conjugate. So plus some another potential which doesn't contain quadratic terms, starting from cubic term of the matrices. Say M cube with some coefficient. Say this is n equal from 3 to infinity. Gn over n m trace m in power of n. So now one can try to calculate let's calculate now partition function as a functional integral from this potential. So considering perturbatively, I am making Feynman diagrammatic technique for expanding this potential by powers, and then considering this part as a propagator. So m alpha beta m alpha prime beta prime is something r minus 1 alpha beta alpha prime beta prime. Formally, I can put here alpha m minus r minus something, get here r. And then what will happen if I consider, maybe I have picture here. Okay, I will have some vertex. 3 m's are associated here, m, for a cubic vertex. I have another vertex, for example, quartic vertex M4 here. So I can make propagator, put propagator between them with R, this propagator. And they have to put another propagator here for any other vertex, and then the third one here, and so on. I will get this picture where here you see those are the vertices. For example, these small ones, the small ones, this one. Different vertices are connected with propagators, which are marked here as R. And you have this type of Feynman diagram for this theory. Now, you see, we have here some lattice where there are rows. This lattice called Manhattan lattice. In this case, it's a random Manhattan lattice. Because on the neighbor lines, lattice links have arrows opposite direction, like driving rules in Manhattan. Therefore, all neighbor parallel lines have a different direction of arrows. The same lattice one could obtain in the previous picture here. This is also random Manhattan lattice. You see this all on parallel lines neighbor, you have an opposite direction of arrows everywhere. There are two types of squares in his lattice. You see, there are squares around which this arrows doesn't allow you to go around, or there is a regions here where you can't go around. For example, this one. This is the wrong position. This should be like this. You can't go around here, and also here, for example. Anywhere here, or for example, and so on. That was this is the same here. You have these small arrows, vertices, and then so this picture precisely corresponds to the red lattice there in the previous picture. This means that with any random Manhattan lattice, I can associate regular lattice consisting from squares, but which is not flat, but the lattice contains angles, contains curvature at different points. And formula for curvature for any angle Rn is p half 4 minus n. If you will associate with each simplex here, with each face here, this type of curvature, and take sum over all faces, take sum over Rn over all faces, then you will get that it's equal to Euler characteristics of the surface, which is 2 multiplied by 1 minus h, number of handles. So in origin, you can consider three-dimensional or any d-dimensional lattice, but regular, consisting from squares, and consider any random surface there. Put on this lattice this picture, construct from that lattice dual one in the following way, like here, and you will get Manhattan lattice or vice versa. There are one-to-one correspondence between them. Surface is always two-dimensional, of course. So, and the statement is, if I will consider this integral over all m's, you will produce all possible types of random diagrams which correspond to all possible random two-dimensional surfaces. And the sum of over Feynman diagrams here is exactly producing sum of the over surfaces. And therefore, this matrix integral reproduces this sum. So this theory is a theory of integrable model given by R matrix, string theory corresponding to that particular theory with R matrix. What kind of vertices? These vertices. These vertices are here. It is in type of product. It is symbolic product, which means you have particular shape of the Manhattan lattice. It's written for particular, this product is written for particular Manhattan lattice. And then you are taking sum over all type of Manhattan lattices. For particular Manhattan lattice, you have a red picture there. You have a vertices, you have a squares there, and everything is there. Here, you see? You have, these are, here you put R matrix, this is vertex, this is vertex, this is vertex. Y number. Wholly vertex I'm associating, well, okay, here there is, of course, sorry. Here there is G. For each vertex is coming corresponding G, of course, in this product. Yes, in partition function, it is that one. Just I am telling that besides these numerical factors, you have a sum over all possible Manhattan lattices, which are equivalent to sum over the random surfaces. And that you have a theory of some theory. For example, you can put any R matrix. You are taking spin as Heisenberg model. Its continuum limit is Vesuminov-Witten model. In this way, you can construct, consider theory of when the Vesuminov-Witten novical is on fluctuating surface. Never considered before. Why I should consider that one? That's a point which I am coming to, and then I will try to calculate this functional integral other way. Why we have to consider, for example, besides Liouville something else? Why I should consider besides Liouville some other anomalies on the surface and analyze them? Because let's consider, for example, simple thing like we have random fluctuating surface x, psi, and fermions there. So I'm considering d-dimensional Chern-Simons fermions, not internal two-dimensional fermions, but Green-Schwarz fermions, external fermions. Theta, they are d-dimensional on this random surface with the action beta, G alpha beta, where G alpha beta is induced metric. And gamma alpha is an induced gamma matrix, induced from d-dimensional set of gamma matrices, which means those are the gamma matrices in the d-dimensional flat space. And multiply by tangent vector, you get induced on this curved space two gamma masses, gamma 1, gamma 2. They're forming gravity. And so you have this here is reparameterization invariant and so on. So if you will calculate now the effective action of this theory, besides the Liouville term, you will get here two other terms, SH plus SA, where H is, so we have d-dimensional space. We consider normals to the surface, d minus 2 normals. We have d minus 2 normals. I is running from 1, d minus 2. And we have two tangent vectors, the alpha x, alpha is 1, 2. So first of all, these tangent vectors are defined up to rotation around inside in the tangent space. So there is an O2 rotation invariant in this definition. And besides, these normals can be defined up to arbitrary rotation SO d minus 2 in a space of this normal part, normal complement to the surface. So calculating the effective action of this theory, so these definitions, these normals and tangent vectors defining so-called second quadratic form and from which you can construct, it's considering as a gauge field, you can define with this Chern-Simons action, which is this one. And since there is a gauge invariance in the definition of these tangent vectors and normals, there is a gauge field A, natural gauge field A, which appearing there. And this is ordinary SO d minus 2 dimensional Vesuminov-Witten model action. So you together for this theory, for example, considering Green-Schwarz fermions, there was discussion that yesterday, Natal discussing that in considering effective action of the Green-Schwarz superstring is hard job. It's nobody actually did it correct finally somehow. It's contrary to bosonic string or Neveu-Schwarz string, when you know what kind of anomaly you should add in order to restore all symmetries and have a series in non-critical dimension. For Green-Schwarz, it's not clear what type of anomaly to do that, how to do that. But these type of terms are there. And in any case, it's necessary to understand, if you consider Chern-Simons or consider Vesuminov-Witten fluctuating surface, how to work with that. So what I am telling here is that if you will consider, for example, our matrix of spin-S-Heisenberg model, which is in continuum limit equivalent to Vesumino model, then you have, in a continuum limit as a string theory, you have strings for Vesumino-Witten model, or strings for Chern-Simons model, as you like. If one can calculate these integrals, then it's clear. It would be clear how to work with this. Simultaneously, we will cross this C equal to 1 barrier because these series have central charge larger than 1. For example, for SU2 level K, you have a central charge is 3k divided by k plus 2, which is, considering second level, it's already higher than 1. So now, that is the motivation why one should consider this type of strings. And since it's hard to move analytically, let's first try to move within matrix model to see what can be done. Yeah, 10 minutes. Yes, any dimension. Yes, no, any dimension. I didn't mention about integrability property that will define some cases, some dimensions which are good one. It's not clear, but there is a way that when integrability, which if there will be time, I will tell what means, in a sense. It means that theory is topological. I will tell about that, but probably I have very little time. If you will consider R matrix, for example, you can put here any R matrix. For example, spin S Heisenberg model, Pabujan model of spin S. Okay, it's in continuum limit. It's after Affleck. It's known that it's defining Weiss-Zumino-Witten-Novikov model. So you put the organized continuum limit at critical point. You have Weiss-Zumino model. That will be Weiss-Zumino model on random fluctuating surface. Or any, you put. In original matrix model, instead of R, identity operators are staying here. No information about integrable models. Here, we explicitly incorporating into the theory R matrix, which define the model as a propagator. And then but it's making calculation harder. Let me in 10 minutes at least give a sketch how it can be what can be calculated in a moment and how. So I would tell that immediately. I don't have a full analysis now of critical behavior of the final theory, but the following stages passed. First, as in previous case, we should diagonalize matrix M by some matrices. So first, suppose we have spin S model. This S matrix of that. So let's consider, so the linear space where the spins are acting is 2S plus 1 dimensional. So I am considering introducing large N somehow, considering unitary theory of 2S plus 1 multiplied by N, and considering Hermitian matrices from this algebra. So my M is this size, 2S plus 1 cross multiplied by N cross the same. So U is from here. So we can diagonalize it. Then you see here the generators of this group can be written as a product of generators lambda A, direct product lambda A with tau I. A is running from 1 to 2S plus 1, and I is running from 1 to N. Those are the generators. So UN, and that's what is the generators for SU to S plus 1. So usually our matrix has a form. It's quite general form. Our matrix has a form as lambda alpha beta some A, IA, lambda A, alpha prime, beta prime. Quadratic it has a formally, you see, 4 legs. In each pair, you can expand over generators of our matrix. I is adjoint I is running the number of generators from 1 to 2S plus 1. Alpha, beta, they are running fundamental representation. So this R, I will multiply now by delta I prime, delta J prime. I can express this product as a tau I, tau K I J, tau K I J prime, tau I prime J. This is the product of these two delta functions, this identity. So if you will, now I'm considering larger, of course, R matrix. I should plug here larger R matrix. I should imagine there is our product of two identities, additional n-dimensional space. Then if you will plug this definition of R matrix into the between this M, after some trivial algebra, you will write this action as M alpha I, A, some lambda alpha A, alpha prime A prime, I A prime, lambda transponated A prime beta, A2 prime beta prime, and M A2 prime beta prime, plus the same function from a diagonal. M's are diagonal elements of matrices M. M, A, alpha. So I have diagonal elements of M matrix, which is from here. It's one can mark as M, A, alpha. Alpha is running from 1 to S plus 1, and A is running from 1 to N. So we came to the kind of Gaussian integral, where instead of group, I would like to integrate now the measure M. I'm dividing as an integral over this diagonalizing matrix U, called sometimes angular variables, and over diagonal elements. So we see that integral, instead of U, I got here lambda, which is a joint representation corresponding to any U. And we have a kind of Gaussian integral over lambda, which is quadratic, but instead of fundamental, the lambda is adjoint. Therefore, there are not free matrices. It's not a quite Gaussian integral. It is from adjoint space. And one is, in order to take integral over this lambda, it's necessary to understand how to integrate over the adjoint space. So then mathematics telling us that adjoint space, the orbits in adjoint space are so-called flag manifolds. Flag manifolds which is full flag manifold, standard notation like this, 1, 1, 1, and 2s plus 1 times n1, which is group U 2s plus 1 n cross U1 2s plus 1 n. So we should factor over the Cartan subalgebra of the larger group, and then this is called flag manifold. And the adjoint representation is this space. This space can be expressed locally, only locally. I'm not considering topology in a moment. One can express as a CP 2s plus 1, 2 minus 1. This complex projective space cross C, P, large P here. 2s plus 1, n, sorry, here, n, minus 3, and so on, up to last one, C, P, 1, as a product of these CP spaces, complex projective spaces. Each of those is sphere twice 2s plus 1, n minus 1, sorry, without that, factorized by U1 subgroup. So then one can, this shows that the measure of integration over in adjoint space can be written as D over all this lambda matrix is equal to D diagonal elements A alpha, and D this factor, and using gauge invariance over U1, because this again this series, you see this factor is gauge invariant again against the U1 group, then we can throw it away because of gauge symmetry, then replace the measure by sphere element. So write our measure over spheres, product over spheres, twice 2s plus 1, n minus I is running from 1 to n. So then we can replace this group, these elements from this space as a sphere elements. Introduce, very good. Replace these sphere elements as normally by delta function. Introduce parameterization of these elements as z alpha a in a way that sum over module square by alpha and a is equal to 1. One can introduce this property as a delta function into the measure of integration, introduce Lagrange multipliers, and incorporate it into the add here as action part. S, I will like L. And then we can replace here these factors by Z. Z alpha A. Here is Z alpha A. And this is now this part. This is pure Gaussian integral because Z now are free parameters. This condition was disclosed by delta as by Lagrange multiplier above. And these are now free parameters running from minus infinity to plus infinity. This is pure Gaussian integral. This integral can be taken, and eventually we will come to the partition function, to the form integral over eigenvalues, integral over some Lagrange multipliers denoted by, just a second, I will look. To write a correct expression, finally, it is large. Yes, the lambda alpha E again. And we have, after diagonalization, so-called van der Monde determinant, which is a product of M alpha, A alpha minus M alpha prime square. I alpha is less than A prime alpha prime, multiplied by some product over M A alpha in power of some S alpha A minus 1, where S I will write what is that. And exponent from the potential, M alpha A, is a product here over alpha A. And minus M alpha A square and lambda alpha A square and some factor z alpha a from lambda alpha a, where z alpha a is equal to 1 over a minus lambda square alpha a half sorry, I here. I is running from 1 to S alpha A, and S alpha A, some number is equal to twice alpha minus 1 to S plus 1 N minus I. So this type of integral from eigenvalues, like in previous standard case, plus integral over some other lambdas, which are scalar, just numbers. And with this type of action, which different from a standard matrix model from above, written above, by this term and by presence of these two terms. So this is the full things I would like to say. This brings integral to the form where now it's possible to analyze critical properties. I cannot trivially repeat, which I told in the beginning, how extracting organizing continuum limit and analyzing multi-critical behavior, because of presence these two terms, especially this one is very strange term. But clearly this object has some critical property. It's hard to analyze, but it should be possible, at least numerical, for example. Anyway, this is the result. And if one could analyze the critical properties, it's possible to calculate, for example, string susceptibility, and that will be the answer for a spin S Heisenberg model, for example. If you will plug all information about model in these coefficients A, which were incorporated into the R matrix. R matrix has a form lambda A, EA, the direct product lambda A, and diagonal elements. So it's a diagonal elements of R matrix. So that is the final things I would like to say. That's it. Thank you.